manually rotated.
Are you recording? Okay, hello Parent 3. We're beginning FTC Day right now. There's one more property of integration. So I'll just call it one more property of integration. And it goes like this. The one more property of integration says something really obvious. So you can add it to the list from the notes from last class. It says that if we take the, here's what it says. If some function f is less than or equal to some function g on some interval ab, then what do you think we can say about the interval? Yeah, then it seems pretty clear that the integral from a to b of f should be less than or equal to the integral from a to b of g. And yeah, that seems really obvious. Why does that seem so obvious? Because it's less. Yeah, there's like less area under a shorter curve, right? So kind of like there's a little bit of duh built into this. If here's my integral from a to b, if f kind of looks like that, and g, let's say g looks like a different function, which is either less than or equal to it. So I'll make it equal in a couple places just for excitingness.
Looks like
excitement. So now that's the g function. The area under the g function is all this green stuff, and of course that's going to be less than the area under the f function. Yeah. Okay. Again, though, I can prove this. How do I prove this? Well, I should take it on a subinterval by subinterval basis. If I partition this interval up into subintervals, and then I choose a sample point x sub I star from the ith subinterval, then it's certainly true. Oh, I think I labeled it wrong, right? No one was even paying attention. This should be f down here, this should be g up here. So it's clear from my picture that f of x sub I star is less than or equal to g of x sub I star based on this, right? This is true. And since this is true, what can I do now? I'm building the integral step by step. What comes next? Multiply by delta x. Yeah, so I'm gonna multiply through by the width of the interval. Since that first inequality is true, based on my assumption, then it's true that I can just multiply through by delta x. Of course, this is true for each subinterval. So I actually have I of these inequalities. So if you have I of these inequalities, you can add them all up, and we get the sum from I equals 1 to n of f of x sub I star delta x is less than or equal to the sum from I equals 1 to n of g of x sub I star delta x. And finally, if one thing is less than another, well, what should I do? What's the last thing I need to do? Yeah, Prem says take the limit. And there's probably like a theorem or something that says if you take the limit of two things, one of which is less than the other, then the limit has to be less than or equal to the limit. And then this is, by definition, the integral from a to b of f of x dx, and this is the integral from a to b of g. Okay, cool. Theorem proved. All right, now I want to talk about something which is sort of like seemingly kind of out of nowhere. What I want to talk about now is the average value of a function. The average value of a function. And okay, so and what I want to talk about is the average value of a function on a particular interval. So suppose I have some function f. We're taking the integral from or rather, we're taking the function on the interval ab, and maybe this function looks kind of like that. All right, and now I want to ask the question. I want to sort of like think about it intuitively first. The question is, how big is this function on average? It's like a question you might ask, right? On the interval AB, on average, how big is this function? I don't have any thoughts.
As big as you want.
No. Yeah, what's a, yeah, maybe I can get some bad answers first. What's a, Josh Park, what was your answer? Yeah, I don't know if he's doing that seriously or not, it doesn't matter, it works both ways. He suggests that the average value of this function is simply the average value of the y coordinates. So just the value of the function at a plus the value of the function at b over 2. That's not an outrageously wrong, well it is pretty outrageously wrong. Why is this wrong? Yeah, Brian. Goes, can I get more than it goes? Also, yeah, what? It's true that the curve is not straight. But I mean, I don't even. We haven't even agreed on what average value even means. So you got to give me more words. Yeah, Haley.
So like, if they both if they both A and B, if A and B are equal, then if it goes up between them, then it's that equation will give you is just the same f of A. Sort of.
Yeah, I guess what Haley is saying is that what this is doing is it's looking only at the value of the function at the endpoints, but that's not intuitively what we mean when we talk about the average value of a function. Maybe it's good to get a particular thing in mind. Suppose this is a temperature graph. Okay. So suppose this is a graph of time versus temperature. If this is a graph of time versus temperature, then what we're doing is we're talking about a particular day. Say A is like, I don't know, A is like 6 a.m. and B is like, 8 p.m. or something like that. And, a day happened and it was like certain temperature and the temperature changed throughout the day. And I guess that's what like happens in like the daytime. The sun comes out, it like gets hotter, then it gets cooler again. And then you get home at night and whatever, you're talking to like your, grandmother or something and you're like, and she asks, hey, what was it like out today? What was the temperature? What kind of day was it? What was the average temperature today? That's the kind of question we're answering. Jeff G.
Is it the integral on the interval divided by the length of the interval?
Oh, Jeff G just said something just out of the blue. That seemed to make some kind of sense to him. Jeff G, yeah, talk about that.
Because like, if you take the integral, like, it's kind of like, you can draw it as a box. The form of the box, and then divide by the length to get it.
Yeah, he's saying all kinds of stuff that I get what he's talking about because I already know the answer. Maybe some of you do too. Let's kind of look again, maybe at kind of sort of the thing that Haley was saying, right? So first of all, right, we can have all kinds of different days. Suppose there was like a really kind of strange day at which, okay, what happens on normal days? On normal days, the temperature starts in the beginning at 6 a.m. at a certain time, and it kind of just goes up and then it comes down again, right? Okay, but then we could have some crazy day in which there was like some sort of it just kind of did this and then it wow or something crazy like that, right? It got really hot. At noon for some. There was some nuclear bomb that went off.
It's when views drop.
Okay. Yeah. All right. So this is time versus temperature. It might have gotten like really hot, and then maybe just cool down again. So this would be a certain day, right? But if you were to just follow the Josh Park formula, then all you would say is that it was a day in which on average it was the value at the beginning. And then what else? Let's take a totally different kind of day where it started and ended at the same temperature, but like now it got really hot really fast and it stayed hot all day and then it got cool again, right? This is a fundamentally different day, which intuitively should have a very different average temperature. And then of course the third case to consider is the very exciting weather event of like cold front comes in and it just gets like really cold all day, and then somehow it gets warmer again at night for some weird reason. All right, so Jeff G was saying something about an integral, and that kind of feels right? Because the integral under this curve somehow is bigger than the integral under this curve. So I feel like integration is like related somehow to this concept. All right, but what I would like to do is, and I think you're basically right, but what I'd like to do is really derive this. How would you do, what do you mean? This is another kind of common sense, but what do people mean when they say the average temperature, actually? Like if someone just asked you, what was the average temperature today, what would you do? How would you like research that? Yeah, Wendy.
It's like the sum of all the temperatures over the sum of like all the times.
Yeah, it's the sum of all the temperatures of all the times, and then just like divided by how many, right? Yeah, it's like a third grade science project. If you had a third grade science project that was like, what was the average temperature on Wednesday, what would you actually probably do? Yeah, take it like every hour. Ryan says, yo, every hour I would get in there, take the temperature, write them all in a little chart, and then I would just sort of average them all. And that's kind of what like a weather app does. If you open up like a weather website or something, it tells you the temperature every hour, and that gives you a good sense of like what the day was like. So I think what Wendy's basically saying is, take this interval, partition it up into equal width subintervals, and then every hour on the hour take a temperature reading. So I look at the temperature now, I look at the temperature now, temperature now, temperature now, temperature, temperature, I think I might have skipped one. Boom, boom. Now I have just a whole bunch of y values, and what do I do with all of these temperature y values?
Add them up.
Add them up and divide by
The number of dots.
the number of them, right? That's just literally what an average is. If you have n, so what we're going to do is we are going to divide the interval a, b into n subintervals. Take a sample point, and we have n temperature readings, and what you guys are telling me is, if I have n temperature readings, the way to average n values is to just add them up and divide by n. So I'm going to claim that by definition of what this means, that the average value, of f on the interval ab is something like just the sum of all of these things. So I take f of x1 plus f of x2 plus all the way up to f of xn, and then I divide by n. Does that seem right?
Yeah.
All right. More.
You could just use like a sum.
Yeah. Okay. So you guys are like, dude, this is like a sum. So sure, I could write this as the sum from I equals 1 to n of f of x sub I times, I guess that's like 1 over n or something. Oh, and also there's one more thing worth mentioning. Why might this be like bad? What if something crazy happened? What if you were doing your third grade science project and you were measuring the temperature every hour, but at 9 a.m. there was a crazy nuclear event, such that it got just after you took your temperature reading, it got really hot, like in that picture over there, and then a giant gust of wind came and blew it all the way. But for about 45 minutes there, it was 9,000 degrees on the face of the earth and burning all livestock and stuff like that.
Why would a science for project matter?
Then a science project, you got to finish it out to the end. So then, by the time your automatic robot, all humanity is gone. By the time your automatic robot took the next temperature reading, it would seem like everything was just fine again, right? So wait, what should we do?
You have to like take a lot of.
We have to I'm just being annoying
maybe
here. Yeah, you just have to take like a lot of, you have to take a lot of temperature readings, right? 1 per hour is not enough. We need to take a lot of temperature readings. How many would you like to take?
Infinity.
Infinity, yeah. So what we need to do here, is we need to add a limit. For this to truly be the average value, then I need to take the limit as n goes to infinity, and so that way I'm taking the temperature readings infinitely often. But the idea is still the same, right? Take n readings, divide by the number of readings, which is n, and then just do that infinitely often. Okay, so what do we have here? What is this? It's a Riemann Sum. Everyone agree?
Oh,
Yeah.
Yeah. Oh. Wait, is it a Riemann sum?
That's the integral.
No.
What?
No, because
There's like not.
Wait, pause, Elijah. Everyone, is this a Riemann sum?
Almost.
Yeah, we have a little problem here, right? It's something's like a little bit wrong, right? If your idea of like Riemann sum is like, I don't know, it's just like a sum or whatever, then you might not be thinking about this at all. But if you really take the Riemann sum concept literally, which I do and so should you, a Riemann sum actually is what you get when you take a function, you partition it up into subintervals, you take a sample point from each subinterval, and you multiply the value of the function on that subinterval times the width of that subinterval. So I have a sum of n things, these are all y values, is 1 over n the width of the ith subinterval? It's like not, right? So something's like a little bit off. This is actually not a Riemann sum yet, because what is the width of each subinterval? Yeah, so the actual, good. The actual width of each interval, this is what you were going to say, Elijah, right?
Yeah.
Okay, how do we fix it? Yeah, Prem's just like, dude, algebra, whatever. If I need there to be a b minus a in there, then we just stick it in, right? And if you put in a b minus a, so now I think I can write this as a Riemann sum. This is going to be the limit as n goes to infinity of the sum from I equals 1 to n, f of x sub I, times b minus a over n, and so I'm going to take out like a 1 over b minus a in the front. And so now, by a little algebra trick, we've converted a sum into an actual Riemann sum. And now, what does this turn out to be? This turns out to be exactly what Jeff G just kind of intuited 10 minutes ago. This is, by the definition of integral, this is going to be the integral from a to b of the function. And then we are dividing by, or multiplying by 1 over b minus a, which is like dividing by the width of the interval. And his kind of intuition here is, you can sort of think about it as like there's all this sort of temperature or something. It doesn't really make any sense, actually. If you this is why I like this example, because it shows how the concept of integral transcends just finding the area under a curve. Because this is a temperature versus time curve. But my claim is that the area under this curve doesn't really make any sense as like a quantity. You guys kind of see what I'm talking about? This is a temperature. It doesn't really make any sense. There's no physical quantity which corresponds with like temperature times time. So, but nonetheless, I can solve this problem with integration. So integration is more than just finding the area under the curve. Integration is the process of adding up an infinite number of infinitely small things. And we've seen that here, if we're adding up a number of infinitely small things, we can use the integral concept for this. How did he know the answer? Because he just kind of felt like you sort of should take all the area. He mentioned something about a box. He said if you take all the area under this curve and then you kind of divide by how wide the curve is, it's like you're forcing this shape into being like a rectangle. Is that kind of what you were talking about? Yeah. So it's like maybe you have a mountain range, right? So let's say you're going hiking and you have some kind of mountain range, and maybe the mountain range looks like that. Okay? So you're going to go up and you're going to All right. And you need to know. So this is the height of the mountain, and this is time. And you want to know, on average, how high is the mountain? Well, if you want to know on average how high the mountain is, because you want to know how much like oxygen to pack or something like that, right? Then you could one thing you could do is you could take all the area under the curve, and then you could divide by the length of the path. And what you're really sort of doing, this is sort of Jeff G's comment, what you're really doing is you're sort of taking all the mountain peaks and squeezing them down into the valleys. So what we have is the average value of a function intuitively is, it's really hard to draw. I think it's like maybe like that. Let's see if I did this correctly. Looks like I didn't. No, maybe I did. does it look like these pieces of the mountain, these blue pieces here, does it look like they fit neatly into, pretty close actually, right?
Yeah.
Into these red pieces here. Yeah, if there's the same amount of area above and below, then that means that this rectangle, not original, but this rectangle, this purple rectangle, is like the amount of mountain there is, or some crap like that, right? Were you to just like wait 10 million years for erosion to happen, or if you just did like West Virginia mountaintop mining or something like that, you would get this rectangle. Okay, and this is the average value of a function. This y value is the average value of f on the interval AB. And it kind of makes sense, right? Because one way to think about this is you have some average value, and let's just call that value like y or something, right? So what this says is that if y is the average value of the function on some interval, then this is kind of what Jeff G was saying, then what that means is that the integral from a to b of the function is equal to y times b minus a. And this is the version maybe that most people find most obvious, right? The average value of a function is the y value, such that if you multiply that y value by the length of the interval, you would get a purple rectangle which has the same area as the original area under the curve. Everyone follow? Some people think of it as you have an ice sculpture, and then the ice sculpture melts. And when the ice sculpture melts, the height of the water, not counting like the various states of the water have different densities. Okay, good. All right, I feel like we get this. All right, this is a good example of us taking a naive concept, that of the average value of a function, writing out what it means, applying the limit process, and solving it via integration. All right, it is also the warm-up for a really important theorem called the mean value theorem for integrals. Oh, that's it. The mean value theorem for integrals. All right, this sounds really important, and it is. All right. Oh yeah, clear your throat. Everyone get ready. The king's out. Okay. What does the mean value theorem for integrals says? Basically what it says is every continuous function on a closed interval has a point whose value is the average value of that function. So I'll write that out. If f is continuous on the interval AB, then at some point C, on the interval AB, the function obtains its average value. F of C equals 1 over b minus a times the integral from AB. Somewhere on any interval, the function obtains its average value. Okay, and the key idea here, this is a sort of a technical proof. It's not actually that hard, but what we need to show is, in other words, something which we see over here, which is if you have some kind of function and it has a certain average value, that there are places at which the value of the function is equal to that average value. Okay, which seems reasonable. Okay, let's prove it. The proof essentially revolves around a simple idea. There are these three pictures. I'm going to sort of squeeze in three pictures here of the same function, drawn in kind of a slightly different way. So here's a function, and let's see. I'm going to draw one function that kind of goes like up, down, up and down, like that. And then I'm going to try to draw the same thing again. Goes up, down, down, up. Okay. Alright, so I would now like to make a claim, which is on the one hand really obvious, but is going to require, these don't look anything like each other.
Or are they supposed to?
They're supposed to be the same function.
They look so good. Exact copies.
That's like fine, right?
No, not really.
You
should
Why is it not fine?
They
Control
don't
C,
start at
Control
the
V.
same spot.
Oh yeah.
Or they don't at the same time.
They're as good as a straight line.
That's, wow. It's harder than it looks. Okay. Good. Okay. So here's my claim. If on the one hand, you just take the area under this curve, you're going to get a certain area. Okay? On the other hand, what if instead of taking the area under this curve, you approximate the area under this curve with a single rectangle, which is the whose height is the lowest y value on that interval. So let little m be the minimum value of the function on the interval AB. And then conversely, let big M be the maximum value of this function on the interval AB. And if we do that, we should kind of want to say that this green area must lie between the blue area and the red area. Yeah? Okay. Alright, so I'll just quickly write this down. I will say let little m be the minimum of f on the interval AB. Let big M be the max of f on the interval AB. Alright, and now this is important enough that I'm going to prove this statement right here. So how can we prove this? It seems so obvious, but we're going to prove it. Okay, well, based on this definition of minimum and maximum, if I take an arbitrary x value on this interval, then f of x should be somewhere between little m and big M. Because that's just the definition of little m. It's the min, big M is the max, so the y value should be somewhere in between those two. Alright, and now I'm going to apply this theorem over here in the left corner, this one property of integration that I sort of forgot about, which is that if a function is less than another function, then the integral is less than the integral. So this little m is a function, it just happens to be a constant function, and this big M is a function, it's also a constant function. So I'm basically going to just take the integral of all three sides of the inequality, which is something that's allowed. Okay, so I take the integral from a to b of this little m function, dx. That has to be less than or equal to the integral from a to b f of x dx. And in turn, that's less than or equal to the integral from a to b of big M dx. Okay. Maybe now some people see where this is going. What can I do now? Someone just mumbled constants. Can you elaborate? Yeah, the first rule of integration from last class, right? Yeah, Prem's trying to say, dude, the integral of a constant is just like you do it, right? Like, what is this? Yeah, this is just little m times b minus a. Okay, cool. And this is just big M times b minus a. Now, anyone got something?
The derivative is
That's the only concern right now.
Wait. Yeah, Kayla.
You can divide by minus
Yeah, that is an excellent idea, which I heard someone else mumble also. Yeah, look, remember, what is it that we're trying to do again? We're trying to show that somewhere this function has the value 1 over b minus a times the integral from a to b of f of x dx. And McKenna says, all right, well, let's just kind of make that expression in there, right? So if I divide all three sides of this inequality by b minus a, then I get that 1 over b minus a times the integral from a to b of f of x dx is in between little m and big M.
Okay.
What's the significance of that? Haley, your head's like sliding away. Yeah.
You've shown that between the min and the max of the function, that it exists that point. One for b minus a times the integral of the function, which is what we're trying to get the mean value.
Yeah, we're trying to show that somewhere on this interval, okay, thanks. We're trying to show that somewhere on this interval the function has this y value. Why should that be? It's continuous and some theorem. Yeah, what theorem? Stuart.
Continuous value theorem.
Continuous value theorem. There's no such thing, but I think you're right. I think you know what you're talking about, but you just don't know what you're talking about. Yeah, the intermediate value theorem. Exactly. This is the intermediate.
Continuous value theorem or something?
This is the
That's what he said.
Yeah, this is the intermediate value theorem, right? Here is the place where the function takes on value little m, right? Let's call that point, like, I don't know, I don't have a name for it. Here is the point where the function takes on value big M. As this function is continuous, if it has value little m somewhere and it has value big M somewhere else, then it must have, it somewhere must be this value. So that's exactly what we do. We apply the intermediate value theorem to f. And we say that this particular y value, so since this y value is in between little m and big M, by the intermediate value theorem, there exists a point C such that the function has this particular intermediate value, and that kind of proves it. Okay. How are we feeling on that? I'm feeling good. All right. What the hell does this all have to do with the fundamental theorem of calculus? What even is the fundamental theorem of calculus? If you don't know, even better. All right. We have these two mean value theorems floating around. Let's compare and contrast them. Here's the compare and contrast. There is the mean value theorem, the old mean value theorem, which we might call the mean value theorem for derivatives. Then we have the new mean value theorem, the mean value theorem for integrals. What do these two have anything to do with each other? Well, the mean value theorem for derivatives says that, well, what does it say?
Oh, yeah.
Whoa.
Oh, okay.
Secant line, tangent line, blah, blah.